Hi everybody, my name's Rob from RobOps, and today we're going to be continuing the EKS experiment series looking into GitOps and how Kubernetes handles good and bad deployments. In this video, we're going to go over the cluster architecture, and then we're going to look at the concept of GitOps and how it works in practice. Then, we're going to set up our experiments to demonstrate how Kubernetes will handle good and bad deployments under load. So here's our architecture. It's a simple two-tiered VPC architecture that will host our EKS cluster. We have a network load balancer that's going to distribute load to our EKS cluster. And we have a CloudFront that's going to act as an ingress to our cluster. Our data layer in this case is MongoDB. For a more detailed view of the architecture and the components, I have another video that goes through the entire setup of the cluster that would be beneficial to watch. The tech stack for this experiment is going to be the same as the previous. We're running a simple Go API that would represent your service or your endpoint. Our deployments are going to be handled by Argo CD and GitHub Actions. Our monitoring is going to be done using Grafana and Prometheus. Our compute and data layer will largely be running in AWS and MongoDB. And we'll be loading the cluster to simulate real user interaction with our cluster using K6. As I mentioned before, the focal point for this experiment is going to be our deployments, and so we're going to be doing a deep dive with Argo CD and GitHub Actions. So what is GitOps? Well, the core concept of GitOps is really that your infrastructure and application configuration are all stored in a GitOps repository. The principles of GitOps are really that it makes everything declarative. So your cluster state can be defined in a GitOps repository, and everything that's in that GitOps repository is reflected in your cluster. By doing this, we make our cluster and its cluster state versioned and immutable, meaning you can only change the cluster state by changing this GitOps repository. This also has a lot of benefits. Things like automated reconciliation become possible. So imagine you have something like a pod that you delete directly on the cluster using your kube control. Well, when Argo CD looks at our GitOps repository, it'll notice that this pod probably shouldn't have been deleted, and it will spin it back up again. In its essence, the concept of GitOps is really you're storing the state of your infrastructure and your application in a Git repository. That Git repository is constantly watched by a controller called Argo CD, and Argo CD will take whatever changes happen in that GitOps repository and apply them directly to your cluster. This ultimately gives you a safer, faster, and more reliable way to operate your cluster. So how does it work? We're going to use an example of a developer who's making a change and they want to get that change deployed to production. So they're going to be working on this change and they're going to commit their changes. They're going to open up a pull request on GitHub. And once that pull request is reviewed, it will be merged. On merge, those changes are going to be synced to our GitOps repository via a GitHub action. And once it's synced to the GitOps repository, Argo CD will be constantly watching, and it will pick up those changes and it will apply them directly to the cluster. So we're going to jump into the experiment. We're going to start with a good deployment. And so we're simply going to make a routine change that any developer or engineer would be making as part of their daily job and their daily workflow. So we're going to load the cluster. And what this means is we're just going to use K6 to put various endpoints under uniform load to simulate a real-world application. Then we're going to jump into the code and make a simple change, open a PR, and then merge that PR. Once that PR is merged, we're going to follow it to our GitOps repository, and then finally to Argo CD, where the change will be synced to the cluster. Once the change is synced, we'll wait for the load test to end, and then we'll observe the load test results. So here's our experiment view for today. On the top right of our screen, we have our Grafana dashboard that's going to be monitoring the endpoints for our API as we put it under load. On our left, we have our Argo CD view with our K8s API in focus. This will show when the deployments happen and the behavior of the pods. On the bottom, we have two terminals. One is going to be responsible for running our load tests using K6, And on the bottom right, we're going to be monitoring the API pods in real time with our kubectl. So with this view, we're going to kick off our first experiment, which is going to be a good deployment. So this is just going to represent a regular change that any developer might make during the day, and we'll see how it syncs to our cluster. So for this change, we're going to go into our code view and we're going to push a change to GitHub that would represent just a regular change as part of anybody's normal day. And then we'll go over to GitHub and then we're going to see the pull request, we're going to approve it, and then we're going to merge it into main. And that's going to kick off a few GitHub actions that will push our changes to the cluster. So if we move back to our code view and we go into K8s API, we're going to just do a simple change here to one of the handlers. We're just going to do the health handler. So currently it's a super straightforward endpoint that says I'm healthy, and we're just going to put hello YouTube as the change. And so on our branch, we're going to go quickly and check out main. We're already on main, which is great. So we're going to git pull origin main to get the latest changes. And then we're going to go git status. So we're going to see we have our change in the health.go. And so we're going to click git add specifically the handler. And we're going to check out -b to changing endpoint for video branch. And then we're going to go git commit -am changing -m changing the endpoint. Or git push origin changing endpoint for video, which is our branch. And then we're going to go and see what that looks like over on GitHub. So here we're going to see that we have a pull request notification. And so we're going to click here and we're going to go changing the endpoint. We're going to create the pull request. Now, before I kick off this change, I'm actually going to switch back to our experiment view, and I'm actually going to start the cluster under load. So this is just going to represent real world scenario as we kick off our merge. So I'm going to click here, and what this is going to do is start loading our cluster. So we're going to have about 10 or so minutes to go through this change. During this time, we should see the load come online on our right side here on our Grafana dashboard. And we should see some activity in our Argo CD UI along with our pods. So we're also going to start watching our pods as we should see some scale up action as well. So we're going to move back to GitHub here. We have our PR and we're going to look at it, and we can see it's a pretty straightforward change. We're just editing a string. So I'm going to give a looks good to me and I'm going to approve. If I was working with more than myself, I would be able to do so, but because I'm just working by myself, I'm going to just squash and merge this. So our pull request was merged, and this is where a few things are going to kick off. We're going to see the sync K8s API manifest to repo action trigger. And what this is going to do is it's going to build an ECR image, and it's going to check to see if any of the K8s API manifests have changed. And then it's going to push those changes to our GitOps repo. So we're going to let this run, and then we're going to hop over to our GitOps repo. And so this is the repository that our Argo CD is watching. And so once this GitHub action completes, we should see a commit to this repository. Okay, looks like the job finished up. And if we click refresh, we should see a commit just landed. And if we see what's different, we see our image has been updated, which is aligned with our understanding because all we changed was application code. If we had changed a Helm chart or something different, we would see more than just the deployment YAML changed. But in this case, an application change, we would expect just the image to be updated. So now that that's done, we should expect Argo CD to pick up this change shortly. So if we switch back to our experiment view, and we look at what's happening with our load test, we can see that we're well into our load test, and we can see that there is some activity with our K8s API pods as well. And as you can see, as I updated the query to SumBy, we can see the load coming online from our load test, and we can see our K8s API pods scaling up. So we're currently at 3 pods. And so what I'm going to do is force a sync. Typically, in these situations, we would see Argo CD sync itself automatically, and that typically happens on every 5 minutes. But we can see that our deployments is out of sync. So I'm going to click synchronize right here, and that is going to bring up some new pods under load. And we're going to see, hopefully, the changes on this new pod that's coming up. And so we can see some new pods coming up. We still have 3, just like before. Now if I go to the details of these pods, I'll notice, or at least I should notice, the SHA on these is in fact 4CF. So if I scroll here, we can see 4CF, and that is the new set of pods. And so I have 4 now as the load test progresses. But what's interesting here is if I go to api.anytimeagile, our new change is now available. And so our change has rolled out under load. The pods have come online and have stayed healthy. So our test has completed, and as we can see, we had 0 interruptions over 3,600 requests. Every single request was served successfully. And if I go over to the details of the experiment, we can see we got 200s across our health, users, post, and compute endpoints. We had about 21 requests per second, 100% completed successfully. Now that we've seen what happens during a good deployment, we're going to do the opposite and deploy a breaking change to our cluster. To do that, we're going to follow the same steps from the first experiment by loading the cluster. Once the cluster is loaded, we're going to deploy a breaking change to our cluster. We're going to watch how that change propagates from our K8s API repository to our GitOps repository and then to our cluster. Once it hits our cluster, we're going to let the cluster operate in a broken state for a few minutes. Then we're going to revert the change and return the cluster to a healthy state. Once the load test ends, we're going to observe the results. Then we're going to do the same experiment again. This time, we're going to increase the min replicas from 1 to 2, and then we're going to repeat the same steps. And then we're going to see what changes that has on the overall test results at the end. And so in this scenario, we're going to intentionally break the API. We're going to push a change that is going to break the endpoint, or at least the API and the service itself. It's going to prevent it from starting up. And what we're going to see is how Kubernetes responds. What we're going to do is put the cluster under load again. And so here, we're going to run the load test again. And we're going to switch back to our code view. So now we're going to go check out -b, breaking change 3. And so here we have a branch called breaking change 3. And we're actually going to go for this into our MongoDB config. And so here, this is where the config is loaded, and it's going to expect certain variables from our secret store with certain names. And so if we say MongoDB URI hello YouTube instead of MongoDB URI, this is going to give some problems to the startup of the application. And so if I go git and I just add the change I made, and I go git commit -m breaking change beware -m breaking change beware git push origin, our branch is called breaking change 3. Great. So now I've pushed this change, and I'm going to open a pull request called breaking change. And we can see here the issue. that is going to impact our API. So I'm going to go squash, merge this, and the same action is going to kick off as before. So here it is. It's going to build the image and it's going to push it to our GitOps repository. And so while that's happening, we'll quickly look back at our experiment view. We can see again that the new load is coming online. But if we're going to go back to our GitHub view, we're going to see this breaking change is merging. Should take about a minute to render and push. Looks like it just finished up. And if we pop over to GitOps, we should see the exact same type of change. We're going from 4CF to 455. And so now if I again go back to our experiment view and I look at our pods here and I look at the details of one of them, I scroll down, I see we're running the 4CF, and what I should expect to see is a 455 come online. And so our first indicator should actually be our API pods that we're watching when they come online. But because I want to illustrate what's going to happen, I'm going to do another force sync here, and I'm going to synchronize the pods, and we're going to see what happens. So we see a new set of pods coming up, and we notice that we get an error. And you can see down below a crash loop. And if I go into the details of this pod, we can see we're in crash loop, running in production, missing required environment variables. So this is our break. We effectively have broken the API. And so we're going to see how Kubernetes responds here. We're going to let the load test run until the burn endpoint's complete. And then we're going to revert the change we just did. And so our CPU burn test has finished. So what we're going to do here is we're going to just pop back over to GitHub. We're going to look at this break and change. And typically in this scenario, you'd be getting some sort of alerts if the cluster wasn't performing properly. And you typically want to revert this change. And so here, we're going to click revert. We're going to create a pull request to revert this change. This is effectively going to switch us back to healthy. And so here, I'm going to go squash and merge, confirm, and merge those changes. So if we go back to, again, our experiment view, we have about 3 minutes left here. So we're going to wait for our GitOps repo to get the new information. And then we are going to sync our cluster. And then once we sync our cluster, we will recover. So here we say 503, temporarily unavailable. We can see a new pod coming up here. And if I quickly cross-check, the version we're looking for is 624, starting 624, the hash. Go down here, we can see 624 came back online, and we can see the cluster kind of came back to healthy. So because we only had one replica, this actually did some damage to the cluster, and we'll see how much damage as soon as this test loads up, but you can actually also see just from the Grafana view here that it doesn't look like the endpoint actually serviced a lot of what was required here. So, or at least all of what was required. And you can see like the health endpoint kind of completely dropped. Cool, so the test finished. And if we scroll up here, we will see some of the results. And we did in fact have quite a bit of failures here. So we did 11,000 requests, about 22 requests per second, and 5,600 of those requests failed, representing about 47%. And so you can see the impact that a bad deployment change could have very quickly on our cluster. Now, if I was running more than one replica, this impact wouldn't have been as severe, because typically Kubernetes will try to keep a replica alive while it rolls out the new changes. But because I only had one replica, I wasn't able to successfully handle the bad deployment. And so what I want to show is what would happen if I had two replicas running instead of one. Okay, so we're healthy, we're synced, and we have two replicas. So now what I want to show is like what happens. What happens when we run that same load test that hurt us before with one replica. So I'm going to start this load test. And in a very similar way, I'm going to go back to our code view. And in this code view, and if I go to config, obviously we reverted the change and pulled the main. So this is now fixed. And if I go git checkout -b breaking change 4, and I again go hello YouTube and save this, and I go git status, and I go git add the config change, and I go git commit -m breaking change again, now with 2 replicas, git push origin, find our branch, I'm too lazy to type it, and I'm going to push this. And so now I'll go to the slides, and I'm going to go to, again, our repo here, pull requests, compare, breaking change now with 2 replicas. If I look at the actual code itself, it's the exact same change. I'm going to complete this pull request. I'm going to quickly review it, and I'm going to squash and merge. So I'll go back to the experiment view as we see the cluster scale up. And so we see actually a new pod has come online to support the increase in load. If I look at our Grafana, we should see that load start to come online. It's starting to uptick here. And so I'm going to wait for the GitOps deployment to finish. And as you see here, like our API is healthy again. So if I refresh here, we can see a new commit. In that commit, we have a new hash, 7f7, and we have some new pods. So actually we see the sync just happen. So we see this new pod coming online, and we see an old pod being taken out. And so in a similar way, we have an issue with this pod. So I look here, take details, missing required production variable. But what's different from last time is we have our old pods running here. If I look at here, when I look at the logs, running in a production environment. And so what's interesting here is, if you look at the bottom right, our cluster is struggling. It's trying to figure out what to do. It can't bring up these new pods because the new pods don't work. However, it does have the old pods. And what's interesting here is it will not bring down these old pods until these new healthy pods come up. In the last iteration of the experiment, one went down and one came up because we didn't have redundancy. And because we didn't have that redundancy, the pods didn't have a chance to fall back onto the previous deployment. And so if I go here and I go anytime agile, we're still healthy despite having a bad deployment. And so I'll wait again until the CPU burn portion of our load test completes, and then I will revert the change that I just did. So our CPU test has completed, And if I go back to our slides and I find the commit that caused us problems here, breaking changes now with 2 replicas, I'm going to click revert and I'm going to create a pull request for this. And as you can see, it's going to bring our cluster back. And so if I go squash and merge, confirm squash and merge, we're going to wait until this reaches our cluster. In the meantime, I'll go back to our experiment view. And again, we can see that the load is in fact going up. And if I do a quick test on our API, we do see it's still available. So in the background, I'm just going to check for this revert to complete. So it's completed. In fact, I'll just sync it now. And so here we go. We see a set of new pods trying to come up. And we do see some running. And there we go. We see the new pods coming online successfully. We see the pods that were in error state get removed or unscheduled. And we see the old set of pods also come offline. So our load test is finished. Let's check out the results. So if we scroll up here, we can see that we did in fact struggle a bit. We dropped 1,300 requests out of 11,000. But if we make that comparison to the previous experiment, we actually did significantly better. In the past experiment, we dropped about 46% of the requests. And in this case, when we had the old serving pods, we did in fact only drop 11%. Now that we've wrapped up both experiments, there are a variety of things we could do to prevent those bad deployments from coming out. Firstly, any PR should be peer reviewed by a peer, and likely that would have caught the obvious breaking change in this case, but sometimes they're not that obvious. And so things like automated testing, automated linting, as well as deploying to lower environments or to canary environments will prevent or reduce the blast radius of a breaking change like this from affecting your customers. With that said, that's going to wrap up the video. Thank you again for watching. If you have any questions, please do comment below. I am very much looking for new ideas for new videos for these EKS experiments. And if you did like what you see, please do consider liking and subscribing. If you want to connect with me, feel free to join my Discord. I post videos there. If you're interested in the work, I have a lot of the setup for these videos on my GitHub page. And I also try to write a more detailed written blog for each of these videos that you can check out on my blog. Thanks again for watching. Please consider liking and subscribing, and have a great week.